Hey guys, welcome back. This is lecture 2 of our thermodynamics series. In this lecture, I want to start your main chapter that is called Pure Substances. I'm not actually sure if that is what the books or your professors will call it, but it is mostly related to phase changes and how pure substances behave. This is also the chapter in which we will be learning about the thermodynamic tables. So feel free to watch back this video as many times as you want because learning to use the thermodynamic tables is quite easy and is something that is in fact required by your course. Like you will not be able to solve thermodynamics unless you're unable to read the tables, right? Before we start, I would like to write a short note on specific properties. Sorry. So you've seen those like specific volume and all that. So what do these mean? Specific volume denoted by small v. It is the reciprocal of density. So as density was mass by volume, it means specific volume is volume by mass. Please note how this is written in small letters and volume, just volume, is written in capital. Right. So we can say that any specific property, quote unquote, specific x is given by that value x over mass. So specific volume, where volume is x, was given by volume over mass. Similarly, if we have specific weight, it is given by weight, sorry, specific weight should be given by weight over mass, but that does not make sense, right? So specific weight, you have to remember alag se, it's given by mass over volume. Similarly, we have specific entropy as well, is given by total entropy of whatever you're calculating over the mass of substance. Specific internal energy is given by capital U by M. This is denoted by small u and this is denoted by small s. So anything specific will be denoted by a small letter. And one last thing that we have is specific gravity. Density of substance by density of water at 4 degrees Celsius. Rho of H2O at 4 degrees Celsius, which is also 1 gram per ml. So in most cases, specific gravity will just come out to be density of the substance. But as such, this formula is good to know, which is why I have written all of these in a pink star. Right, so with that being said, now we can move on to our chapter which is called Pure Substances. Okay, so I have now fixed the screen looking oversaturated. Apologies for that. It's something to do with videos on iPad and videos on Windows. Anyways, as I was saying, we have now started the chapter Pure Substances, and in this chapter we're going to mainly learn about four things. First of all, we're briefly going to look at pure substances, what they are. Then we're going to look at the property table and phase change, because these two are closely interrelated. Phase change. We're going to have a look at the ideal gas equation. And finally, we're gonna have a bit of an introduction to enthalpy, although this is not used until much later in the course. Okay, so let's begin. So we're gonna start with pure substances. Not much to cover here, just a few definitions. Bulk of the chapter is in the phase change part. What is a pure substance? A pure substance is substance that has a fixed chemical composition throughout. A fixed chemical composition throughout. So, my question to you is air a pure substance? I would like you to pause the video and think about it. In regards to this statement, is air a pure substance? Yes, air is a pure substance because even though it is a mixture of different gases, the composition of those gases, the composition of gases that are in the air, example oxygen, nitrogen, bit of argon, other gases, is constant. The composition of gases does not change. So that means air is a pure substance with regards to this definition. That was mostly it for pure substances, not much there to tell you. Now we come to the important part, which is phase change. This is where a lot of the thermodynamics comes from because it is actually the study of phase changes, how change occurs in nature. So, we're gonna study the phase change of water first because it is the simplest substance. Phase change of water. Okay, so first of all, how does a phase change in water occur? There's water over here in this, and this is a piston, right? Not gonna write piston right now because I have to copy and paste this diagram a bunch of times. Just give me a second. Okay. So this water is at 25 degrees Celsius. This water is at 30 degrees Celsius. This water is just below 100 degrees Celsius. This water is just above 100 degrees Celsius, which is what these signs over here represent. This water is now properly above 100 degrees Celsius, and this water is a lot above 100 degrees Celsius. So let's see what is actually happening here as we are heating up the water. So at 25 degrees Celsius, this is room temp. This is just all liquid. Then as we go to 30 degrees Celsius, we can say that it is subcooled. It is subcooled here also, but since this is our base point, I'm using some other temperature to explain. It is subcooled or compressed. This means that it is not about to vaporize. Not even close to vaporizing, right? Because 100 degrees Celsius is when it is about to vaporize. At 100 degrees Celsius, we say that it is a saturated liquid just below 100 degrees Celsius because it is just about to vaporize. It is very, very infinitely close to vaporizing, so which is why it is a saturated liquid. That means no vapor exists and all of it is in liquid, but that liquid is just about to be converted to a vapor phase. At 100 degrees Celsius, some of the liquid has started to vaporize, so some form of vapor does exist. So now we have liquid and vapor both in the container. This is called saturated liquid vapor mixture, or we can just call it a saturated mixture. At 100 degrees Celsius, at a bit greater than 100 degrees Celsius, in fact, all the liquid has been converted to vapor. So, in fact, we can put all the vapor dots here. So, this is all vapor. However, something interesting happens here. This is not that much more than 100 degrees Celsius. This is still close to 100 degrees Celsius. Something interesting happens here. If we suddenly remove this heat, all of this vapor will start to condense back into this form, right? Because that is what happens when water goes below 100 degrees Celsius, it will start condensing back, right? And since this is also very, very close to 100 degrees Celsius, it will start condensing. So, this point is called as saturated vapor. All of our form is in vapor, but if we remove the heat, it will start going back into its previous state. That is, the droplets will start condensing back into the vapor mixture. And if we don't remove this source of heat, and the temperature goes much greater than 100 degrees Celsius, example 120, 150, whatever. In fact, we'll see very, very high temperatures also, but that is besides the point. This is called superheated vapor. Now, why will this not start condensing? It's because the temperature is very, very greater than 100 degrees Celsius. It's not close. So, first it will cool down, then it will reach 100 degrees Celsius, then it will go back here, then it will go back here. So, this is not about to condense. Not about to condense. And this is about to condense. If we remove the heat source. So this is how phase change in water, the simplest substance, happens. Let's just go over it once again. So at temperatures below 100 degrees Celsius, whatever they may be, we have a subcooled or compressed liquid, because this is not about to vaporize. At just below 100 degrees Celsius, we have a saturated liquid that is just about to vaporize. Means if we supply even a bit more of heat, it will start vaporizing. At just above 100 degrees Celsius, we have a saturated mixture. We have supplied heat and some of it has in fact vaporized, so they exist in a mixture. At around the same point, we have saturated vapor. When all of the liquid has been converted into vapor, please note that the temperature between these two will not increase, because energy will first go to converting the liquid to the vapor rather than increasing the temperature. If you remember, that is how we got our latent heats of fusions and vaporizations and all that. So the temperature difference between these two is not that much, right? So first all of it will get converted into saturated vapor, and it is just about to condense. And then finally, if we have converted all of it into vapor and we keep supplying heat, now there is nothing to do but to increase the temperature. So the temperature will increase and this will become superheated, and it is not about to condense. It will be beneficial to see what this process looks like on a graph as well. So let us do that. This graph is very, very important because we will use it to determine the phase of almost every known substance. It is called a TV graph. And in fact, we'll be seeing quite a few variations of this. We'll see a TV graph, a PV graph, and A couple of more which are quite important. You must keep this graph in mind at all times, right? So it relates the temperature and small v. Remember that small v is the specific volume during phase change. This point is the point of saturated liquid. We will see why that is. This point is the point of saturated vapor. Here, liquid and vapor exist simultaneously in the container. This is a superheated line, superheated vapor line. Whenever I say superheated, please remember superheated vapor is the implied meaning, because a liquid cannot be superheated, only a vapor can be superheated. So this is superheated vapor. This is compressed liquid, also called as subcooled liquid. Subcooled. And one more thing to notice is this line represents latent heat of vaporization. Because notice that the temperature during this process is constant. During this process is constant. So temperature is not increasing. You're just supplying heat to change the liquid to vapor. So latent heat of vaporization. Also, this region is called sensible heating region. However, that's not very important. Now this is specific volume. So it is meter cube per kg. Remember, because over here we were talking about specific things are divided by mass. So kg. This is capital V is in meter cube and mass is in kg. So specific volume is in meter cube per kg. An important thing to note is that phase change takes place at constant pressure. Right. So we've seen this graph, and now let us try to relate it to what is going on over here. So let us look at this region first. Let me choose a different color. How about green? Let's go with green. This region first. So this region is called the compressed liquid region. So this region relates to this part of the diagram. Yes, diagram. Then we go slowly along, increasing the temperature until we reach the 100 degrees Celsius point, or just below 100 degrees Celsius, right? And you can see this point is of saturated liquid, and that is because it is just about to vaporize, and we had called it a saturated liquid. Then we keep slowly heating it, but the temperature does not increase. Why is that? We saw that is because some of the liquid gets converted into vapor first, which is why this line also represents the latent heat of vaporization, right? So then we keep heating it, and then we have a saturated mixture because vapor and liquid exist simultaneously, which is what we have written here also. Liquid and vapor exist simultaneously. And then if we keep heating it, all of the liquid has been converted into vapor. So now there is just vapor, which is the saturated vapor. All of this is vapor. This is vapor. And this is just about to condense, because see, if we remove the heat from this point onwards, then this point will immediately fall back to here and we will start getting liquid. So it means that this vapor is just about to condense back into liquid. However, if we do not remove the heat, then the temperature keeps rising and we get a superheated vapor. So I really hope that you understood how this graph works, because it is quite an important graph. It is very useful to determine what state a substance is in. And in fact, in the following tutorial, we will also be seeing how to determine the state of the substance using this graph and in conjunction with the thermodynamic tables. Okay, now real quick, let's just have a look at saturation, temperature and pressure. And what they are. Right. So we know that boiling point of water is 100 degrees Celsius at 1 atmospheric pressure. So this 100 degrees Celsius is called saturation temp, Tsat, and this is called saturation pressure, Psat. And the relation between these two looks something like this. For pure substances, remember this chapter is entirely about pure substances, and in fact, most of our thermodynamics will be dealing with pure substances itself. So I think, yep, this is Tsat and this is Psat. Now I would like to have a more detailed look on this graph as well. We will start uh, identifying regions in this graph and what they correlate to. Right now we have only identified lines and points, but now we'll be looking at entire regions of this graph, right? Okay. Okay, so if we see here, these are the lines. These lines are called constant pressure lines, by the way, because remember, phase change, if you're drawing a TV graph, then the phase change will take place at constant pressure. So these are called constant pressure lines. And this temperature is in fact Tsat, because this is the temperature at which the saturated mixture exists. So in fact, we can say that inside this region is the saturated mixture region. You can also say that beyond this, all of these lines are of superheated vapor. Let's just mark this point. We'll get back to it later. So this region is called a superheated region because you have vapor exists. This in fact extends all the way to this very special point, and we'll name it later on. And behind this region is called the subcooled region, remember, because beyond this everything is in liquid. Right, and now let's get back to talking about this point that separates these two regions. This is called the critical point. we notice a very interesting phenomena at the critical point, that is, if we try to draw a line, it'll almost be parallel, So that means we're having no latent heat of vaporization whatsoever. So at critical point, LV, this is what I'll be using from now on, is 0. It's also worth noting that these lines are not exactly straight, it is something like this. However, we draw them straight for the purpose of convenience. Uh, yeah. So now let's do a quick question that will help you better understand the concepts. Let me just write it down. Okay, the question goes 1 kg of saturated liquid water. Saturated liquid water. So, what does that mean? Where is our water on our TV graph? So, if this is our line, our water must be at this point because this is the saturated liquid point. Is being vaporized at two different temperatures, 100 degrees Celsius and 120 degrees Celsius. Now, how do we know that where these uh, temperatures are? It can be here, it can be here, it can be here. In fact, it can be anywhere on this line and still have different values of temperature, right? So, how do we know where the question is telling us to take the temperature at? So, if we read it carefully, we can see it is being vaporized. Being vaporized. That means from this point, we are going towards this side. So that means the temperature must be at this line itself. Okay. So as it is being vaporized, it means it must be at this line at two different temperatures, 100 degrees Celsius. So let us just mark this as 100 degrees Celsius and 120 degrees Celsius. So this is the higher temperature, 120 degrees Celsius. Now clearly we can see that the length of this line is longer than the length of this line. So this is longer and means it has more LHV or LV. Therefore, 100 degrees Celsius water requires more energy due to higher LV. And intuitively also this makes sense because if you look at it, if your water is already at 120 degrees Celsius, that means a lot of it is already in the vapor phase. So to convert the remaining into vapor phase, you will require less energy as compared to 100 degrees Celsius where the water has just started to vaporize. Okay, so now let's talk about the critical point. Please note that this graph is not quite symmetric and your marks will get deducted if you draw it perfectly symmetrically. So it happened to me, don't draw it perfectly symmetrical. And this is called a supercritical fluid. I know right now it must seem very confusing, so I encourage you to watch the tutorial after this lecture as well to clarify what exactly is going on and if you need this theory, and when you do, how to apply it in practice. So the points about supercritical point, as we saw, LV is 0, and since there is no LV, saturated liquid and saturated vapor are the same. Okay, so now let us look at the variation of that previous graph, the phase change TV graph, this graph, and call it a PV graph. So now temperature is constant. One thing to note here, that we said that if phase change takes place at constant pressure, then we get this graph with the constant pressure lines. But what happens if phase change takes place at constant temperature? Like over here, we have a constant temperature. What happens if phase changes during this? What happens if we increase the pressure while we are somewhere on this line? How would we represent that? So let's do that. Interestingly, it is a similar shape. However, the graph is now completely flipped. It is also worth noting that our regions, however, do remain the same. So this is still your subcooled region, and this is still your superheated region, and this is still your mixed region, that is liquid and vapor, and this is still your supercritical point. So now this is your saturated liquid line and this is your superheated vapor line. Sorry, saturated vapor line. So not much to say. Just remember this graph and the temperature volume graph, and that will majorly get you through this chapter. And as pressure is constant here, these lines are called constant temperature lines. An interesting thing to notice, let me just label these 1, 2, and 3. T1 is less than T2 is less than T3. Similarly, over here also, 1, 2, 3. P1 is less than P2 is less than P3. So the higher the line, the higher the pressure. And now we will be moving on to the ideal gas equation. So take a break here if you want, but I do recommend watching the tutorial class before we move on to the ideal gas equation. Or you know what, I will tell you about this in the next lecture. Watch the tutorial class after this, rewind this lecture if you have to. I know that my explaining is not the most linear, but I hope that if you solve the tutorial while carefully listening to the problem solving process, then you will be able to completely understand everything that I have told you in this lecture. The phase change of water diagram is one of the most important ones to understand conceptually, theoretically, and intuitively. So I hope you devote a bit of time just thinking what is going on in this diagram and trying to relate it with this diagram, right? Because this diagram is the one that we use to determine the phase of almost any substance. So that's it. See you in the tutorial lecture after this. And after that, we'll be talking about the ideal gas equation.